everyone, welcome back to the channel. I hope you all are doing great. So from this particular video, we are starting is with the previous year questions of your UPSC Geoscientist exam. So as you know, in the UPSC Geoscientist exam, we encounter the various questions have been asked. Like you encounter the questions from your organic chemistry portion, your physical and your inorganic. Along with that, your analytical chemistry questions are also being asked. Right. So here what we are going to do is separately for each of these topics that are being asked in your exam, we will be discussing the various questions that has been asked in your previous years, like from the year 2020 to 2025, we will be discussing. So firstly, we are starting this with our organic chemistry portion, and this is gonna be the part number 1 of this particular series. So like this, the various parts, it will be in various parts, we will be covering our organic chemistry portion. In the similar manner, we will be discussing in various parts about the physical chemistry, your inorganic and the analytical chemistry portion we will be discussing on this particular channel. Okay, so before starting this particular class, if you are coming to the channel for the first time, make sure you subscribe to the channel and do hit the like button also for the video if you understand the concepts of this particular class, and do share it with your friends as well. Okay, so now let us begin with the first question of this particular series of your organic chemistry, right? So the first question is there on your screens. Firstly, if you want to try it yourself, you can see it, and then you can have a look that what procedure, what I am following to solve this question. Okay, so the first question we have is that which cationic species it is more stable in each of the following pairs. So two of the pairs have been given to us. One is we have named as the pair number X, and the other is your pair number 1. In each of this pair, two species have been given. So cationic species means it refers to the fact we have to look upon to the stability of the carbocations. Right. So for the carbocations, for the carbocation, that your cationic species it is stabilized in the order that your tertiary carbocation it is more stable as compared to the secondary one, and then is the primary one. The reason for this it lies in the fact that the tertiary carbocations, that means the carbon on which the positive charge it is present, it is further attached with the 3 alkyl groups. This is my tertiary carbocation. Secondary means the carbon in which the positive charge it is present is further attached with the 2 carbon atoms. And primary means the carbon on which the carbon to this cationic species is present is further attached with the one of the alkyl groups. Right. So these three differ in their stabilities based upon the electronic vectors which is being with which we all are facing. So in the tertiary substituent, if you see tertiary carbocation that you are having, it will be maximum stabilized because of the hyperconjugation and the inductive effect of the alkyl species that are attached to it, followed by the secondary, and least we will be seeing that the primary one will be least stabilized. Okay, so this is gonna be the order, and along with this we generally observe is this, that my allylic and the benzylic carbocations that we have, allylic and the benzylic carbocations, they have the more stability. Alkylic means you have this type of the species. This is called as your allylic carbocation, and benzylic it means on the benzene ring. This is the species and the CH2, and here is your positive charge it is present over here. These are more stabilized, reason being is the resonance present in them. So this is an overview of this particular concept. So now let us see that in these two pairs that have been given to us, how is the stability of the carbocation is going to be varying. For the pair number X, if you see, here the initial in the molecule number 1 that is given to us, the carbocation that is present, here the carbon that is bearing the positive charge is further attached with the one more carbon atom, right? So that means it is my primary carbocation. And even if I do its resonance over here, like this, the resonance can be done. So the resulting molecule that you will be observing is, here the double bond it will be shifted, and at this position you will be getting is the CH2, and here will be the positive charge, right? So again you can see the carbon on which the positive charge it is coming is further attached with the one more carbon atom. So this is again you are getting is the primary carbocation. That means in the molecule number 1 that I am having, here only the primary carbocation we are gonna get even after the resonance stabilization we are providing it, right? Whereas in the second molecule, if you see, Here initially you will see in this particular molecule the carbon on which the positive charge it is present is further attached with the one carbon atom. That means initially it is my primary carbocation. Now if I do its resonance, that means this electron density we are shifting. So this means we will be getting here is this double bond, it will be shifted, and at this position your positive charge it will be coming. Right now on this carbon center, that is bearing your positive charge, it is further attached with the one carbon and the two carbon. That means here the secondary carbocation is getting reformed. And we know that the stability order for the carbocation is that your secondary carbocations, they are more stable as compared to the primary one. Right? So that means in the molecule number 1 and 2, your second molecule, it is gonna be more stable. Right? So among the options you can see it, that try to eliminate the options and solve this question. So here in this the first option it says that the first molecule it is more stable as compared to the second one. So this option we can cancel it out. Moving upon to the second one, you see here again it is saying that the first one is more stable. So again you can cancel this out. So that means out of the C and D our answer is gonna be there. Right? Now let us discuss about the next pair that is given to us. So this I am rubbing it because I want to discuss the next molecule now. Okay. So the next molecule it says in the third molecule if you see here the positive charge is present upon the nitrogen atom, whereas in the fourth molecule if you see positive charge is present on the oxygen atom. Now you see that a positive charge on a more electronegative species it is gonna be less stable, because electronegativity it means that it is highly electronegative species, they like to bear a negative charge over there. So electronegative species with the positive charge, it is highly unstable. So in this, if you see electronegativity comparison, if I do, that is for the oxygen, it is more as compared to the nitrogen, right? So here it is gonna be, so here it is gonna be that my electronegativity of the oxygen is more, because left to right as we move the electronegativity it in a period when you are moving the electronegativity it increases. So oxygen is more electronegative as compared to the nitrogen, which means that the positive charge on oxygen, that molecule it will be less stable, and the other one it is gonna be more stable. So this one third one it will be more stable, because nitrogen as compared to the oxygen is less electronegative. So as compared to oxygen, its positive charge it will be stabilized. That means here in this particular options, the most stable one will be the third molecule. That means second from the first pair and the third from the second pair will be having the as the answer, which refers to the fact that my option number D is the correct one. Okay, so I hope this question is clear to you. So now let us move upon to the next question we have is this one. Okay. So in this question they are stating is that which one of the following molecule is non-aromatic. Focus upon the statement. They are asking about the non-aromatic species. So firstly, what is meant by the aromatic species? Let us look upon to that. So for a species to be aromatic in the nature, it should be it should follow certain properties. That is, it should be cyclic in the nature, right? From the benzene you can see its comparison. Benzene is your aromatic species, right? So it is cyclic in the nature. It should be planar in the nature. Planar refers to the fact that where the carbon atoms that are present, it should be having the sp2 hybridization, or it should be your sp hybridized, right? So planar it means sp2 or sp hybridized. In the benzene molecule you can see all these molecules, they are my sp2 hybridized, right? That means it is forming three sigma bonds and one pi bond. So 1, 2 and 3 sigma bonds and one pi bond. This carbon atom it is forming. So it is my sp2. Similarly, if you will be seeing all the 6 carbon atoms in your benzene will be your planar species, that is they are having the sp2 hybridization. Okay. Next is they should follow the Huckel's rule. Huckel rule. So what does my Huckel rule? It says that whenever a system I am having that is cyclic, conjugated, and it is planar in the nature, at that point it should possess the 4n plus 2 2n 4n plus 2 pi electron. It should be present in this, where n can be my 0, 1, 2, 3, and like so on. Various integers are possible in this. Okay, so this is the condition for the aromaticity. When one of the condition of this is not satisfied, like The anti-aromatic, if you want to see the comparison, anti-aromatic. In the anti-aromatic, you will be seeing the species will be the cyclic, they will be planar, but they gonna follow the 4n plus pi electron rule, they will be following, right? When any of these one conditions it is not obeyed, the species that you get, it is your, and this is, they are called as your non-aromatic species. Okay, so like this only, using these rules we can compare between these four molecules that have been given to us. In the first molecule, if you see, it is your naphthalene molecule, and you can see the species, it is my cyclic, right? So cyclic it is there, it is planar, that is all the carbon centers here are my sp2 hybridized, and it should follow the Huckel's rule. So count the number of the pi electrons that are present in it. So number of the pi bonds, you can firstly count it out: 1, 2, 3, 4, and the 5. So 5 pi bonds I am having. So it refers to the fact that in total that I am having is 10 pi electrons it is present. So if I keep n value to be equal to the 2, so my order it will become number of pi electrons 4n plus 2, right? So it will be 4 into the 2 plus 2, that becomes your 10. So 10 pi electron rule, so 4n plus 2 pi rule, it is being obeyed. So this is my aromatic species, right? Now, so that means A is gonna be my aromatic. So this is not gonna be our answer. Next one, if you see here, and this is your cyclopentadienal system you are having. So here also, if you will be seeing that 6 pi electrons are there which are involved in the conjugation. One is from this negative charge that is present over there, and this pi bonds that are present in this. So they are in the conjugation you are having. It is cyclic, planar, and it is following the Huckel rule as well. So that is, you can see when you keep the n value equal to the 1, Huckel's rule it will be obeyed over here. So 4n plus 2, 4 into the 1 plus 2, that will be equal to the 6. So 6 pi electrons, it is following the Huckel's rule, and that is being obeyed over here. So this is gonna be my aromatic species, right? Now, moving upon to the C molecule. So here you see that my species, it is cyclic in the nature, right? So here it is planar because sp2 hybridized species are present in this. Now count the number of the pi electrons in this. So you see 1, 2, 3, 4, and the 5. All of them, they are in the conjugation. So in total 10 pi electrons. So just like the naphthalene molecule, you might be thinking that this is gonna be aromatic in the nature. But in HL, what you observe is that these hydrogen atoms which are attached to this particular position, they are gonna be, these hydrogen atoms that are present, they are gonna cause the repulsion, and due to that the structure it does not remains to be the planar, and that means one of the condition of the aromaticity here it is not being satisfied. So that means our species it becomes the non-aromatic, right? So that means the correct option will be this one, because we wanted to find the non-aromatic species, right? You can confirm from the B option also, that is cyclic, planar, and where the 4n plus 2 pi electron rule it will be obeyed. So that is gonna be your aromatic. The correct answer to this particular question will be your option number C. Okay, so I hope this one is clear to you. Now, let us move upon to the next question that we are having is this one. So this says that the orthoparadirecting effect of the methyl group in the electrophilic substitution reaction of the toluene. So what is basically our toluene? Toluene is your benzene, right? Like this, and to this the methyl groups have been attached to it, right? So they are asking that this toluene it is your orthoparadirecting in the nature, but what is the effect which is involved in this? Okay, so here the methyl group, you can see, you can represent one of the hydrogen atoms like this. So here I am having is, I'm writing it as CH2, and this is H, right? So you can see this sigma bond electron density that is present between the carbon and hydrogen. This electron density we can transfer it. So whenever a sigma and a pi bond it is in the resonance, like this the pi bond it is gonna be in the resonance. So due to that you will be seeing that here the negative charge will be coming at its ortho position. So you can see like this, you will be seeing this here the negative charge, and here like this double bond CH2 you have got it, and that H it has, this bond it has broken, so this H it has left in the middle. So this particular resonance is present between a sigma bond and a pi bond. So this type of the resonance that you observe, not the resonance, this type of the conjugation that you are observing in the case of the sigma bond and the pi bond, this is called as your hyperconjugation effect, right? Inductive effect, that is due to the electronegativity it arises, just the electron pulls you observe, electron pull you observe it. Hyperconjugation effect is the non-bond resonance like this between the sigma bond and the pi bond. When the resonance is present, this is your hyperconjugation effect. The resonance effect, that is when you observe this conjugated system if you are having. So in this the pi bonds it is present, or the lone pair or the double bond is in the conjugation. That type of the effect is called as your resonance. Okay, and electromeric, you can say the mesomeric effect it is there. So like this, if you have the OMe species and to this your CH2 positive species it is present, here the oxygen it bears the lone pair of electrons, it can provide this particular electron density can be provided and will be stabilizing your carbocation. So this is my electromeric. In case of the methyl group that is present in the toluene, here the sigma bond that is between the carbon and hydrogen and the pi bonds of the benzene ring, they are in the conjugation, you can say. To this effect is my hyperconjugation effect. Okay, so B is gonna be the correct option for this. So moving upon to the next question now. So this is the one. So let me just zoom this if it is not visible. So here in this question they are asking is the relative order of the basicity of the following amines they are asking for us. Okay. So basicity, what does the term basicity it means to us? So basicity it means a base species, that is a base is the one that has the ability to donate the electrons. Donate the electron pairs. Electron pairs. That means there should be the availability of the lone pair of an electron that should be present on a particular molecule that it can donate to act as a base. Right? So in this particular four molecules, we have to compare their basicity order, that which one is gonna give its lone pair of electrons at a faster rate and which one is gonna give at a smaller rate. So each of this species, you see that there is a presence of the nitrogen atom is present, and then we have to see where there is more availability of the lone pair of electrons on the nitrogen center. That species it is gonna give its electron density. That means it is gonna act as a base at the faster rate. In the molecule number 1, 2 and 3, if you see, here the lone pair of electrons that are present on them, these are involved in the conjugation like this. They are involved in the conjugation. In each of these species you can see they are involved in the conjugation. The extent of conjugation where this resonance or the conjugation with the benzene ring it will be different based upon the various substituents that are attached to it. But all of this they are involved in the conjugation. Right? Whereas in this fourth molecule if you see it is your tertiary amine, nitrogen center having the lone pair, and to this the 3 alkyl groups are attached to it. That is your ethyl species have been attached to it. Now ethyl species, as I said, they can apply the inductive, they can apply a inductive effect, they can apply it like this. They will be donating the electron density, right? No doubt here is with Walden inversion is observed in this case, that due to that there will be some sp2 conversions from this sp3 to the sp2 conversions you will be encountering. But as compared to the other molecules, if I see it, this one is gonna donate its maximum, it has a maximum electron density on it that it can donate to the other species, which means its basicity as compared to the other three ones in which the nitrogen pairs are not available upon them, they are involved in the conjugation. The fourth one is gonna be the of the maximum basicity. That means in our order, fourth one molecule it is gonna come at the most basic order. It is the most basic one. It is gonna be there, right? Now in the other three, if I see 1, 2, and 3, resonance is there. But as I said, the impact of this resonance that is present in them it is different. Their magnitude it is different. On the various factors it is dependent. So let us observe these factors now. In the molecule number 1, if you see, here at the ortho position, this methyl groups are present, right? That is gonna create the repulsion, right? So due to that, what happens is this carbon nitrogen bond that is present between the benzene ring and the nitrogen center, it goes out of the plane because of this repulsion which is being created by these methyl groups, right? So due to that, what you will be observing is this nitrogen bearing the lone pair, it is not much involved in the conjugation with the benzene ring, because resonance it will be possible when it is in the plane. But due to this steric factor that is present at the outer position, it will go out of the planarity, and you will be seeing that this is gonna give out of the plane it is going. So the lone pairs are present on the nitrogen center and is available for the donation, right? So that means it is gonna come at the second position, and it is gonna be of the second number priority in the basicity order, right? Moving upon to the second and the third question, if you see here, there is presence of the aniline molecules are there, but in the third molecule you see here is a presence of the NO2 group, which is my electron withdrawing group. By its minus M effect, it withdraws the electron density towards itself, right? So if it is applying its electron withdrawing effect, it is applying. So due to that, what is gonna happen, this nitrogen, it is gonna feel more amount of the push towards this towards this NO2 group. The electron density it will be provided like this. The benzene ring it is present. Let me show its resonance. Okay, so this is the molecule you are having. Here is this NH2 group it is present, and here is this NO2 group, N double bond O, and here is this O group it is present like this. So here you will be seeing the nitrogen, it will provide its electron density. This goes over here, and this one it is going over here. This pi bond it is shifted over here, and then this electron density it is coming to this oxygen center. So due to that, what you will be seeing is on the oxygen center a negative charge it will be coming, and that is gonna be more stabilized. That means this NO2 molecule that you are having, this provides a more push towards itself of the electrons. That means NH2 group in that the nitrogen containing this lone pair availability it will be lesser one. That means it is gonna be the least basic among all of this. So that means the third one will be coming at the least priority, and second one will be present before that. So 4, 1, 2, 3 is gonna be the order for the basicity. I hope the various factors which are involved in describing its basicity, I am able to make you understand that. Right? So now let us move upon to the next question. Next question you have is this one. Again, let me just zoom this for you. Okay, so in this they are saying is that which of the following pairs it has a higher dipole moment. Okay, so dipole moment basically you mean is it is in the magnitude. If you see, it is charge into the distance. So here this is the factor, that is the charge you are encountering. Okay. So in this again two of the pairs have been given. Among these, in the first molecule, if I observe it, here is this 3-numbered ring it is present, and here is this double bond it is present, and here is this carbonyl species that is present, and two of the methyl groups are attached like this. So this carbonyl group that I am having, in this there is a presence of the carbon and the oxygen atom. They differ in their electronegativity, so that we can present it in this particular form as well, like this. Here you can see it will be O negative, and here it will be the positive charge present over here. Like this you can present this carbonyl group. Reason for that is, if you see, if I presented in this charged form, the species that I am getting after that, this one, it is aromatic in the nature. Reason being, you can see it is cyclic in the nature, right? All the carbon atoms that are present in this particular ring, they are your sp2 hybridized, and it also follows your Huckel's rule. You can see it is 4n plus 2 pi electron rule it should be obeyed, right? So here if I keep the n value to be 0, so 4 into the 0 plus 2, that means 2 pi electrons are present. That means if I present the carbonyl group in the form of the charged species, here I am getting is a ring which is my aromatic species. That means this particular ring it prefers to be present in this particular charged form, right? So for the dipole moment we needed is this charge presence over there. So that is being formed in this case. So that means this one is gonna possess the dipole moment. Whereas in the similar other molecule, if you see, that is in the molecule number 2, here you will be seeing that if I present it in the charged form like this, O bearing the negative charge and carbon bearing the positive charge, based upon their electronegativities, this charge separation it has been done. the species that I am getting after that, it is just a three-membered ring and here a positive charge is being formed over here. So you can see this is not my aromatic species, right? So here there is gonna be less dipole moment, that means it will be present in this particular carbonyl form only, whereas the first one molecule that I am having, it will be present in the charged species, O bearing the negative and this bearing the positive charge. That means among the 1 and 2, your one molecule that is present, it is gonna have the more amount of the dipole moment as compared to the another one. Okay. Now in the pair number 1, similar way we can proceed it. So if in the molecule number 3, I break the charges like this, if I break it. So here your 7-membered ring, it will be having the positive charge and this one, other one, it will be carrying a negative charge. So this will have the positive charge and this will carry the negative charge. So after that, if you see, the 7-membered ring, it has been formed like this. This is the species and this is your aromatic in the nature. Again, you can check all the rules. It is cyclic, planar and it is following your Huckel's rule. Whereas the other ring that you are getting, this is negative charge and here this negative, this double bond and a negative charge it is present. So this is not my aromatic species. Reason being, you can check it that there are in total 4 pi electrons are there. One is from this, 2 electrons are coming from this negative charge and 2 is coming from this pi bond. So Huckel's rule is not being obeyed over here. That means this particular molecule that we have formed, it will not prefer to be present in this charge form. It will prefer to be existing in this particular format only. Right. Now let us see in the molecule number 4, if I break this charges. So here if I bring this electron density shifting, I do it like this. So in this case I will be getting is a 7-membered ring like this. Here a positive charge it will be present and the other species that I have got, it is my cyclic 5-membered ring and this bearing a negative charge. So both of these species after the charge separation, if we are creating in this, they are getting this, which we are getting is a formation of the aromatic species. So both of this, they are your aromatic species you are getting. So this is gonna have the more amount of the dipole moment as compared to the third molecule because here the charge separation it is arising over here. Right? So the reason for the charge separation is lying in the aromaticity factor. Okay, so that means our correct option will be 1 and the fourth one. So that means your B option it becomes your correct answer. Okay, so I hope this one is clear to you. So now let us move upon to the next question that we have is this one. Now this question it says, again on the basis of the carbocation stability, the question is being asked to us. So we are saying is, which one of the following carbocations is not expected to rearrange? So whenever a rearrangement is taking place in a carbocation, that is on the fact that you are getting is a more stable carbocation. In the first question only that we discussed, this one on the basis of carbocation stability, here the rearrangement it was possible because from the primary you were getting is the formation of the secondary carbocation, right? That was the more stable carbocation. So whenever a rearrangement that takes place, that is due to the fact you can get the more stable species formation whenever you are getting it. At that point, the rearrangement that takes place in your carbocation, right? So now in this case, the molecule number 1, if you see, here the CH2 species that is present, this carbon is further attached with the one carbon atom. That means it is my primary carbocation. Right? Now if I want to do the rearrangement in this, there is presence of the hydrogen atom in it. So I can do the 1,2 hydride shift in this. 1,2 hydride shift I can do it. So after that, what species I will be getting is, here you will be getting is the methyl species and a positive charge at this particular species, right? So that means here you see now the positive charge that is on the carbon center that we are having, it is further attached with the 3 carbon atoms, this one, 2 and the 3 carbon atoms. So that means it is my tertiary carbon center I am getting. So that means after shifting I am getting is a more stable carbocation. So rearrangement it is occurring in this particular case, right? Next one molecule if you see, here is the methyl group and this positive charge is present over here. So this carbocation that we have got, it is the secondary carbocation. Reason being this carbon bearing the positive charge is further attached with the 2 carbon center. So this is your secondary carbocation, right? Now in this case, the rearrangement, if I do it, from this side the hydrogen atom that is present, we can do the 1,2 hydride shift in this, 1,2 hydride shift. So after that, the molecule that you will be getting is like this. This is gonna be a ring, and here there will be the presence of this methyl group, and this hydrogen group we have shifted on this particular side, so positive charge is coming at this particular position. So here if you see the carbon that is carrying now the positive charge is further attached with the 3 carbon atoms. So this is my tertiary carbocation I am getting. That means this rearrangement it is again gonna occur, right? Next, C molecule if you see, this is the allylic species. So this one is my secondary carbocation I am getting it. If I do the rearrangement in this pi electron density if I shift in this, I'm gonna get here is this particular molecule. The ring will, if this double bond it will be present, and here you will be getting this CH2 and a positive sign it will be coming because this pi electron density it has shifted. So this carbon here it will be carrying a positive charge. So this carbocation that you have got it, this is your allylic carbocation. This is your allylic carbocation. That means after the rearrangement, I am getting a more stable carbocation. So this rearrangement is again gonna be occurring. Right? Now in the next molecule, if you see in the D case, the carbon that you are having, it is carrying a positive charge is attached with the 3 carbon atoms. 1, 2, and the third one. So this is my already a tertiary carbocation in this. If I try to do the rearrangement in this, I will be getting a less stable carbocation. That means no rearrangement it will be taking place in this. There will be no rearrangement. And this is what we wanted to look upon, no rearrangement. Right? So this is what we wanted. So that means our correct option to this particular question will be the D. Okay, so I hope this one is clear to you. So now let us move on to the next question that we have is this one. Next question it is saying is classify the following species as your electrophiles, nucleophiles in the organic reaction. So various molecules have been given to us. We have to see which one are the electrophiles and the nucleophiles. So before that, what is meant by an electrophile and what is meant by a nucleophile? Let us focus upon to that. Electrophile. Electrophile. The word electrophile, it means the electron loving. It is made up of 2 of the words. The word electro, it means your electron, and phile, it means the loving. So those type of the species which are electron loving. So which species will be loving the electrons that are itself being electron deficient in the nature, right? So that means electrophiles are those which are my electron deficient species. Electron deficient species, right? So which type of the species can be my electrophile? They can either carry the positive charge or there can be presence of the vacant orbitals in them. It can be your d orbital or your p orbital. So these are your electrophiles. Whereas the term nucleophile, the word nucleophile, it is again made up of 2 of the words. The word nucleo, it means the nucleus, and phile, it means the loving. It means the loving. So nucleophilic species are those which are your nucleus loving species. So which species will love your nucleus? Nucleus, it contains your protons and your neutrons are present. That means it carries a positive charge. So that means the electron rich species are my nucleophile. Right? They are having the excess of electrons. So these are the basic things that you have to focus upon. Now in the various molecules you have to see which one is your electron deficient species and which one are your electron rich species. So the first molecule you have is SO3. Now in the SO3 there is a presence of the vacant d orbitals in this. So this is gonna be your electrophilic in the nature. Okay. Next is Cl with the positive charge. Cl positive, it means it is your electron deficient. So again, this is my electrophile in the nature. Next is NO2 positive. So this is again and positive charge pairing species. So this is your electrophile. Next is CH3NH2. Here in this you can see nitrogen, it bears a lone pair of electrons on it. That means this electron density it is available for the donation. That means it is electron rich species, so this is my nucleophile. Next is H3O positive. So your H3O positive, again oxygen atom is bearing a positive charge over it. So here it means it is your electrophilic in the nature. Next is BH3. Again, if you see, there will be presence of the vacant p orbital in this. So this is again gonna be your electrophile, right? Next is Cn negative. So it is bearing a negative charge. So it is your electron rich species. So this is my nucleophile. So that means CH3NH2 and your Cn negative are the nucleophiles. Remaining are your electrophiles. So these you can check it in your options. And also you can perform it using the elimination method. BH3 in the first case, if you see, they are saying it is your nucleophile and that is not gonna happen. So this option you can cancel it from here. Next one you see SO3 and the BH3. Again they are saying BH3 is my nucleophile and that is not possible. Right. Next one, in the third case, you can see CH3, NH2 and your Cn negative. They are my nucleophile and the remaining are the electrophile. This is what they are saying. And this one is a true statement because you can see nitrogen, it bears the lone pair of electrons, and cyanide, it is carrying a negative charge. So it is your electron rich species. So the correct option will be your C1. Okay. Again, you can see in the D option also, cross-checking it just. So BH3 and SO3, they are my electrophilic in the nature and they have marked it in the nucleophilic option. So this one is not gonna be the correct answer. So the C1 is the correct option for this particular question. Okay. Moving upon to the next one, we have is this question. It says, which one of the following molecules it does not exist as the mesoisomer? So now what is meant by the mesoisomer? Okay, let us focus upon to that. So basically mesoisomers are the molecules in which there are more than one chiral centers you are having. Chiral center means the carbon center bearing attached to the four different species it is attached. That means it is chiral in the nature, but that particular molecule it is optically inactive. The reason for the optical inactivity lies in the fact that it contains either the plane of symmetry in it or it contains the center of inversion is present in this. So these are your characteristic of the meso species. Examples if you want to see, like this if you see, this is the species I am having. Here the CH3, OH, here you can see this is OH, H and this H species. So suppose this is the molecule you are having. So you can see two of the chiral centers are present in this. Right, so we expect it to be the optically active in the nature, but it contains the plane of symmetry present in this, like this. This is the plane of symmetry. You can see reflection will be there of this particular two chiral centers and the methyl groups that is present, right? So due to this presence of plane of symmetry, it is your meso compound. So that is what you have to focus upon now, that you have to see which of the following molecules is not a mesoisomer. That means the one in which there is not any presence of plane of symmetry or your center of inversion is present. So there is two of the possibilities you can see. If you are able to observe the plane of symmetry in this wedge dash form, it is okay. But if you are not able to see it, you can make the conversions of it in your fissure projections as well. Okay, so we are gonna discuss in this particular form only. Okay, so in the molecule number A, if you see molecule A, if I see it, so you can see we can pass a plane of symmetry from this particular center, this particular carbon center, we can pass the plane of symmetry. You can see here the bromine groups that are present in this particular centers, they both are at the wedge positions. That means they both are gonna reflect each other when the plane of symmetry it is passed through there. Right, so that means this plane it is present in there. Okay. Next is, so this is my meso compound. So this is our meso. Next molecule if you see, again from this particular carbon center you can observe this plane of symmetry, you can pass it. So both of the bromine atoms they will be reflecting each other. So this is your meso compound. Okay. Next is, if you see in this particular case, the molecule number C, you can sit at the center of this particular molecule. So either you can check the plane of symmetry or the center of symmetry present in the molecules. Either of this symmetry elements, whenever it is present, the species it is my meso. So here you can see in this at this center when I am sitting, going at an angle of 180 degrees to the one another. So you can see here this bromine atom I am encountering at the back of it, and here I am encountering the bromine atom in the front of it. That means here is a presence of center of inversion in this. This is what is meant by the center of inversion. In group theory you might have learned about this. So due to the presence of center of symmetry in this, it is again your meso species, right? Whereas in the D molecule, if you will be seeing, there is no center of symmetry present in this, because if I see it sets it at the center of this particular molecule, here this bromine atom it is present in the wedge position, which means it is in the front side, and the other bromine also it is in the front side only. Center of symmetry it is possible in the C molecule when one of the bromine is in the wedge position and other is at the dash. But when both are at the wedge or both are at the dash, this center of symmetry it is not going to be present. So this is not your meso species. This is not meso. Also you can see there is no plane of symmetry and no center of symmetry. So due to that fact it is your not the meso species. So that means the correct answer it will be your D molecule. Okay. Moving upon to the next question now, we have is this one. So here it is asked that which of the following molecules does not have a plane of symmetry present in them. So again, the symmetry elements only we have to check it. So either you can do it in the wedge dash or you can do it in the Fisher projection conversions you can make it, or in the Sawhorse also you can do it. For this particular molecule we will be seeing all of this conversion and will be solved. Okay, so in the A molecule, if you see, it is given in to us in the wedge dash. Firstly, we will be forming the Sawhorse formation for it. So this carbon center that is present, this one, this you can present it as this particular. This is the Sawhorse projection for it, like this. Okay, so to this, at this particular position, my ethyl group it is present. Okay, because this carbon center it is in the inverted form. Okay. Firstly, focus upon this carbon center. Here is this ethyl group. Now here this hydrogen atom is at the wedge position. So if I look from this particular side, this particular species it focuses upon to the wedge side of it. So this is gonna be the presence of, there will be presence of hydrogen on this particular side and chlorine will be on this particular side. Whereas in the other case, if you see this type of the Y, it is present over here. Here the ethyl group, it is in the planar species, right? On the wedge side, you are having is the presence of this Cl, and the dash side, the presence of the hydrogen atom is there. So this is its Sawhorse projection. Okay, you can convert it into the Fisher projection to check its plane of symmetry, or you can check it here also. So let us just convert it into the Fisher projection. For that, you want that both of them, they should be in the eclipsed conformation, right? So for that, around this first carbon center that we have labeled one, we are gonna do is 180 degrees inversion. So for that, what we do is we just interchange this particular positions. So you will be getting is this particular molecule. Correct? While you will be getting this ethyl group, it will be coming over here, and this H and this Cl, they will be interchanging their position. This Cl, this carbon around this carbon center, no changes has been done. So this is its eclipsed conformation we have drawn. Now in the Fisher projection, you can have it like this. So the first carbon, this one, this carbon center, it is labeled at the bottom one. In this particular species, if you observe, the ethyl group it is present in the planar side. This Cl group it is present on the wedge side and on the right side. So this will be present over here, and this hydrogen atom it will be present on the other side. Okay. In the second molecule, that is this one, this carbon center, if you will be observing, here again your ethyl group it is present on the planar side, Cl is present on the right side, and this hydrogen atom it is present over here. Right. So now you can observe in this particular Fisher projection that you have drawn it, there is a presence of plane of symmetry in the molecule. That means if you pass this particular plane over here, this is the plane that you have passed it. So you can see this chlorine atom and this chlorine atom both will be reflected. This hydrogen atoms will be reflected, and this ethyl groups they will be also reflected. So this is in the Fisher projection you are observing it, and in this particular conformation it is the easiest one to observe your plane of symmetry. Rather than this, If you want to see in the other conformations that we have drawn it, that also you can see it. We can see that in this particular Sohor's projection that we have drawn it, both of them they are in the eclipsed conformation. That means one behind the another one. So this plane of symmetry you can see, this plane you can pass it. So ethyl is encountering the ethyl group. This Cl group present on the right side, this is encountering the Cl on the right side, and here the hydrogen atoms they are also encountered. Okay, even if you don't want to go in the eclipse conformation in the Sohor's projection, you can check it in this particular form as well. The first one that you have drawn it. If there is presence of center of symmetry in the molecule, the plane of symmetry it is definitely gonna be present over there. You can see it that if you sit at the center of the molecule at this particular position, you can see at an angle of 180 degrees, one ethyl group I am encountering, I go backward in the 180 degrees direction, again ethyl group I am encountering, right? Again you can see in this side if I go it, in the front position hydrogen atom I am encountering, and at the back position also if I am doing at an angle of 180 degrees, again hydrogen group I am encountering it, right? That means similar environment is present. Again, if you see in this particular direction, if I am going in the front side, the Cl group it is present, and here on the backward direction, that is at an angle of 180 degrees when I am moving. Again, the Cl group it is coming, and this time it is at the back position. So there is a presence of center of symmetry in this. So either it is plane of symmetry. If center of symmetry it is present, definitely the plane of symmetry is present in it. So either of the three options you can opt it to reach up to your conclusion. Okay, so that means in the first molecule plane of symmetry it is present, right? Now in the next molecule that you are observing, it is now again given in the wedge dash position only. You can convert it into the Sohor's, or in the Fischer projection you can convert it to see if the plane of symmetry it is present in it or not. Okay, so this is the molecule you are observing, and here is this at the dash position the presence of the hydrogen atoms that will be there, right? So let us firstly draw it into the Sohor's projection. So at this particular carbon center, this inverted Y position I am having. Here is this ethyl substituent it is present. So this one is your ethyl substituent. Right? On the wedge side there is presence of the Cl, and at the dash side there is presence of this hydrogen atom. And on the another carbon center, if you observe it, this type of the species. So here is presence of the ethyl group. On the wedge side the Cl is present, and this side the hydrogen atom is present. You can in check the center of symmetry in this particular case if it is present or not. You can see if I am going in the planar species ethyl group, I am seeing that at the 180 degrees it is present. But here in this case, if you will be seeing that the chlorine atom here it is present in the front side. But on going in the backward direction, in the opposite direction when I am going it, I am encountering is the hydrogen atom over there. That means in this case no center of symmetry it is present, because whenever center of symmetry it is present, similar environment it should be present at an angle of 180 degrees, and here different atoms since we are encountering, so that means center of symmetry is absent over here. Even you can convert it into the Fischer projection to cross check your answer. The first carbon atom, this one I am taking, we wanted it into the eclipsed conformation. So again 180 degrees inversion you can do it. After that you will be seeing ethyl group it is coming over here, hydrogen over here, and Cl over here. In the other case, the second molecule that I am having, it is already present in the erect Y conformation, so that one only I am using over here. So this one eclipse conform, this Fischer projection I have got it. So you can see there is no plane of symmetry present in this. No plane of symmetry, because if you try to pass it over here, this hydrogen is encountering the chlorine atom over here. So no center of symmetry it is present over here. So here the statement is also being confirmed that whenever center of symmetry it is absent, plane of symmetry it is also absent in that particular case. Right? So one more thing, in the eclipsed conformation, that is in your Fischer projection, we never check the center of symmetry. Never check the center of symmetry. So this you can see, you might be thinking that in this particular Fischer projection, when I am going at an angle of 180 degrees, I am encountering is the center of symmetry I am encountering. But this you are forgetting, it is in the eclipsed conformation. So in that, in the Fisher projections, we never check the center of symmetries like this. Okay. So you can check only the plane of symmetry in your Fisher projection, but never your center of symmetry. Right? So in this particular molecule, there is no plane of symmetry, and this is what we wanted. So you can confirm it from your rest of the options. In the C molecule, you can see they are at these two chlorine atoms, they are present 1 and 4 position. So this plane of symmetry, it can be passed through this. In the D molecule also, from this particular center, you can pass the plane of symmetry. So both these methyl groups which are present at the wedge position will be reflecting one another. So they are reflecting one another. So there is a presence of plane of symmetry. So the correct answer, it becomes your B option, that there is no plane of symmetry present. Okay. So I hope this one is clear to you. Now moving upon to the next one, we have is this question. It says, which of the following amino acids it is achiral in the nature? That means in which of the following amino acids examples they have given to us, which of them there is achiral, that means no carbon center it is present, which is having the 4 different substituents attached to it. Right? So to solve this question, you should have an idea about the structures of the amino acids. Right? So here the various, so 20 amino acids basically are there. For them, each of their structures you should have the idea about that. So I'm going to discuss about these 4 that have been given. So first one is the alanine. You have the glycine, proline and the valine molecule. So what basically is an amino acid? Amino acid basically it means you have a carbon center. To this one side you have the presence of the NH2 group. On the other side you have is the presence of the COOH group, and here is the presence of the hydrogen atom, and this R group it is present. So this R basically it keeps on changing based upon that the presence of the which type of the R group you are having, various names are given to the amino acids. Alright. If you have look upon to the structure of the glycine molecules, the simplest amino acid that you have, this looks like this. I am presenting it into the Fisher projection. This is NH2. You have here the COOH, here the hydrogen atom. Here in the glycine, the R atom is your H only. So this is the structure of your glycine molecule. Okay. This exists in this bitter ionic form. I am not going into the details of the amino acid. Just I want to focus upon its structure. Okay. So glycine, here the R group is the hydrogen atom. So you can see in this particular carbon center that I am having, here one is this NH2 group, other side the COOH group, and the two of the hydrogen atoms are present in this. That means this is achiral in the nature. Achiral in the nature. So it is not having the carbon center which bears the 4 of the different species are attached to it. So for the confirmation, let us look upon to the structures of the remaining of the amino acids also. The glycine has been done. Next is about the alanine. In case of the alanine, your R group, it is your methyl substituent. So this species NH2 you will be having. So basically in the exact form, that is the natural appearance that you see, COOH will be here, this NH2 group will be here, here will be R group, and here you will be seeing as the methyl. So the presence of this methyl group is making this alanine molecule. Okay, so in this particular molecule you can see it is your chiral center, it is present because 4 of the different substituents are attached to it. So this is your chiral in the nature. Chiral in the nature. Next is, if you see the valine molecule, valine, the valine molecule you see, you will be again there will be change in the R species that is attached to it. Here you have this COOH, on this side you have the NH2, this is the hydrogen. In the case of valine, you see here the CH3 species and here this methyl group it is present. So this is the structure of your valine species. Okay, so again you can see this carbon center that you are having. This is again your chiral species that you are observing. So this is again my chiral amino acid. Next molecule that is given to us is your proline molecule. So proline molecule that you have, proline, it contains your 5-membered ring. It is present in this. this nitrogen center it is present, and on this particular carbon center you have the presence of the COOH and this H group it is present. So the rest are these double bonds, they are present in this. So this is my proline molecule. Okay, so again you can see all this double bonds might not be there. So again you can see that here will be, this is again your chiral species it is present over there. Okay. So that means among all the amino acids, in fact among all the 20 amino acids where you will be observing it, glycine is the only molecule which is achiral in the nature. Rest all of the amino acids that you observe, they are your chiral in the nature. Okay, so this is the one. Okay, so among all the amino acids, glycine is the only molecule which is your achiral. Rest all of the amino acids are your chiral in the nature. One correction you can make it over here. This double bond presence it is not there. Okay, so make sure you learn all the 20 structures of the amino acids that are there. Okay, so now let us move upon to the next question. So the correct answer it will be your glycine over here. That is your achiral in the nature. Right. Moving upon to the next question we have is this one. So this says that consider the following compound, that is A has been given to us. We have to look upon to its enantiomer. Okay. So enantiomers basically it means the stereoisomers you are having. They are having the non-superimposable mirror images of it. So for the molecule that has been given to us, it is my CH3. Here this species, bromine is present. Here the hydrogen atom. Here the methyl group it is present. Here the hydrogen atom, and you can, here is CH2, CH3 is given to us. So we can draw its mirror image. So I'm placing the mirror image in this. So like this, I'll be having the mirror image of it. So left it becomes the right and right it becomes the left. So this methyl group it will be reflected on this particular side, and the hydrogen it will go on this particular side. Methyl it will be present in the plane, and here this Br it will be reflected on this particular side. The hydrogen it goes on to the another side. So this is the exact structure of the enantiomer, that is the mirror images of this particular molecule, that is non-superimposable over it. That is, if you try to take up this particular molecule and place it over to the another molecule, that is its mirror images, you will be seeing they are not gonna be superimposing over one another. This is the meaning of the enantiomers. Now among this you have to find it out the four options that have been given to us, the correct answer that is that one. Okay. So in the molecule number 1 that you are observing, here is presence of the methyl group, hydrogen on the right side, Br on the left. So the first carbon center chirality it is matching, but on the other carbon if you are observe it, on this right side there is presence of the methyl group, but in my mirror image there is presence of the hydrogen atom, right? So ethyl group is over here only. So this can't be my mirror image. That means it is not the enantiomer of your compound number E, because it is not your mirror image, right? So this is not the correct one. Moving upon to the next one, next option that you are having. So in this case, methyl group it is present. Br is present on the this side, that is your left hand side it is present. Hydrogen is on the right side. This one is matching. Next one that you observe, CH3, this ethyl group and the hydrogen atom. Try to do the rotation in this, because ethyl group try to bring it into the bottom side. So if I do the rotation in this particular cases like this, the conformation of it I am drawing it. So that will look like this. CH3, here the H, here the Br it will be present, and here this methyl group it has come to this particular position. Ethyl group it has gone to this particular side, and this is my hydrogen species. So now try to tell your answer. So again, you are not encountering the exact mirror image. The methyl group is at the bottom, but the methyl and ethyl they are at the opposite position. That means even after the rotation, that is drawing its conformation, I am not getting the exact mirror image. So this one is again not my correct answer. Now the C option, if I observe it, here the first carbon center methyl group is present, bromine on the left, hydrogen on the right. So this center it is matching. But the other carbon, again the rotation has to be done, because ethyl group is present on this particular side. Try to bring it into the place of the methyl group. This methyl, it will be shifting on this side, and this hydrogen, it will be going over there. So we will be getting here is this particular species. Hydrogen, here the Br, here the methyl group you will be observing. Here there will be presence of hydrogen and the CH2, CH3 it will be present. So try to check your answer. Again, I'm not seeing that the correct confirmation I'm getting. Here the methyl group is on the left hand side, but here on this particular molecule it is present on the right side. So again, C is not my option. Right. Now focus upon to the D molecule. In this case, you can see in the second carbon, this methyl group is in the correct conformation, that is on the left hand side it is present, hydrogen on the right and methyl in the bottom. So this is the correct representation. But in the above side also, let us cross check that if we are getting the correct conformation. So again, rotation has to be done in this. So in this the rotation, if I do it, methyl group will be brought over here, Br it will be moving over here, and the hydrogen group it will be shifted over here. So its correct conformation you will be having is, I'm drawing it on this particular side, that is on this corner. I'll be getting here is the methyl group. Okay, in the bottom one is the same CH2 CH3. This is the hydrogen methyl group I'm having. Next is, instead of the this methyl group, here the hydrogen it will come, and at this position the Br group it will be present. So you can see these two are my exactly same structures I am getting over here. So that means this one is the correct enantiomer of my given compound. So that means D is gonna be our correct option. Okay. So now let us move on to the next question. So we have is this one. So this says we have to find the total number of the optical isomers that are possible for the given cholesterol structure. So for the, to see that how many number of the optical isomers are present, look for the number of the chiral centers, and 2 raised to the power of that n. N is the number of the chiral centers that you have, number of the chiral centers. This will give you the exact number of the optical isomers that you are getting. Okay. So in this particular cholesterol molecule that is given, let us see the number of the chiral centers. The one in which the OH group is attached, this is my chiral center. You can see it is having the 4 different arrangements, are 4 different species are attached to it. One is this OH group, hydrogen, this CH2 on this particular side, and then this carbon I am encountering on this side. Here this CH2 and then the CH2. So this is my chiral center. So this one is gonna be your number 1. Next is, you can see this one will be the number 2 you will be seeing, because again you can see one is this methyl substituent, one is this chain it is going, and other is this CH2 group, and here is this methyl group. This is the species that is present where the double bond it is present. So this one is gonna be the number 2 carbon center, that is chiral. This one is your number 3 chiral center you will be observing. Again you can check the presence of the different groups that are attached over here. This one will be your number 4. This will be number 5. This will be number 6. This is number 7 chiral center. And this one is gonna be your number 8. So in total, I'm getting here is the 8 chiral centers are present in this. That means total number of the optical isomers in this case, it will be 2 raised to the power of 8. That on solving, you will be getting this as 256. That means for the given cholesterol structure, the number of optical isomers, it will be at 256. Okay. So let us move on to the next question now. So the next question we have is this one. It says consider the following groups that are attached to the achiral carbon center. So some carbon center is there. So this 4 of these different groups have been attached to it. So what is the decreasing order of the priority of the above groups based upon their CIP rule? Okay. So to get the RS confirmation, you have to follow is your CIP rule, right? That according to which the preference order it is given, that the atomic number it is given, the higher preference atomic number. That means if you have a carbon center to which the 4 different groups are attached, suppose the fluorine, chlorine, bromine and the iodine. The highest priority is given to the center which is having the maximum atomic number. Among this, it will be your iodine. So that means atomic number preference is to be done. Then you will be seeing the various rules you might have encountered. Then you focus upon its mass number, then you see it, and then the remaining one. So let us see the various attachments that you are having. So here is this first position it says we have the carbon triple bond, this alkyl group, alkyne group it is present over here. So this double bonds replacement you can do it like this. If one of the double bond I am replacing it, I am gonna get as a phantom atom over here, right? Next is if the next double bond I am removing it. So here you will be seeing the carbon atom. It goes like this. On both the sides, the carbon atoms addition it will be done. Right. So this is the actual species that I am having after the opening of the double bonds that are present in it, because the phantom atoms have to be present over here. So you can see that to the alkyl group, if this particular species it will be attached, this carbon center that is present, it will be attached with the one carbon, two carbon, and the three carbon centers it will be attached to it. Right. So this is the first species that is given. Now let us look upon to the second one that you are having. It says CH with the CH3 twice. That means we are having a CH. This is attached with the two of the methyl groups like this. That means this is attached to the carbon center. If this one is attached to my carbon center, this species, this carbon is further attached with the one carbon and the two carbon atoms it is gonna be attached, right? So this is the first one and this is the second one, right? Next is the third molecule that is given to us. It is just your ethyl species you are having, CH2 and your CH3 it is present. So this is attached to your carbon center. So the carbon here it is attached with only one of the carbon center, it is further attached to that. Now in the fourth molecule here you are having this alkene molecule it is given. Double bond CH2. So again double bonds are present. You can present it into the form of the phantom atoms. So here when the double bond I am removing it, so the carbon atoms will be added on both the sides. So that means this species is attached to the further carbon atom. So this carbon atom which is attached on this chiral center that we will be getting, it is further attached with the one carbon atom and the two carbon atoms. So that means here you can see both all the sides the substituents are your carbon atoms only. So when the substituents are the same, we have to look upon to the various number of the species to which it is further attached to. Right. So here in the first case, if I am observing, here this is attached to the three of the further carbon atoms. That means the highest priority will be of the first species, that is my alkyne group that is present. Right. So that means the first one is gonna be the maximum one. So from that, your C and D options you can eliminate it out. Next one that I observe it, that this third molecule that is present here, the carbon center to which is attached to the chiral center is further attached with the one carbon atom only. So that means it is gonna be of the least priority. So that means third one will be having the least priority. So A is gonna be your correct option for this particular issue. Okay. So I hope this one is clear to you. So now let us move on to the next question. This is the one. This says what is the correct configuration at the carbon number 2 and 3 in the following compound? So a molecule is given to us where the carbon centers are labeled as second and third. We have to give them the RS configuration for this. Okay. So I'm expanding this molecule CH3 twice it is present. Okay. Here the OH group it is present. Here the methyl group it is attached. And here is this. This is the second carbon. So the stain it is undergoing like this. So this is the ethyl substituent attached over here and this is the Cl. So firstly around the second carbon atom, if I observe it, so highest priority it is given to the atomic numbers, right? So that means among this oxygen molecule it has the maximum atomic number. So this one will be given the highest priority, followed by the nitrogen atom that is present, right? Then you see this is also the carbon atom. This one is also carbon atom, but this one carbon center it is further attached to this Cl. So that means this one will be given the next priority, and this one is gonna be the least priority ones. So go in the order of this 1, 2, 3, 1, 2, and 3. It is going in the anti-clockwise direction, right? But here you can see the fourth priority that I am having. It is present in the horizontal line that you are having. So this R, this confirmation you have to change it. So this will become your R configuration. It will be doing. That means at the second position I am having the configuration as the R configuration I am having. Right. So that means from this particular case we can cancel out our second and the fourth option we can cancel it out because they are saying at the second position S configuration you are having. So that is not the correct one. Right now for the similar way we have to look for the third center, that carbon center that they have labeled. So this is NCH3 twice that is present. Here is this OH group. Here is this methyl group. In this case there is presence of this Cl methyl group. Here this ethyl group it is present. Okay, so now around the carbon number 3 we have to focus. Among this the chlorine it has the maximum atomic number, so this one will be given the highest priority. Right. Now in this case methyl will be given as the least priority because this is just the methyl group that is attached. No further attachments is present in this. In the case of ethyl that I have written, so this basically it means you are having the CH2 group. This is further attached to this methyl group, right? And here also this carbon atom is attached, which is further attached with this OH group. That means this one will be given as the second priority, and this CH2, CH3, this will be given as its third priority. So now let us rotate this 1 to 2 to 3. If you are seeing, it is going in the anti-clockwise direction. So S configuration I am getting it, but the methyl fourth priority group that is present again on the side. So this will be again inverted. So this will become your R configuration. So that means at the second position also R was present, and at the third position also the R configuration I am having. So third is gonna be the correct answer to this particular question. Okay. So now let us move up on to the next question. We have is this one. So again configurations you have to find it out. You have to give the EZ nomenclature to the following molecules. EZ means Z means when both the higher priority groups are on the same side, they are on the same side, and E we give it when they are present on the opposite side. That is higher priority groups are present on the opposite side. So in the molecule number 1, if you see on this carbon center, out of the iodine and bromine, iodine it will be having the higher priority and bromine it will be having the second priority based upon the atomic numbers. And on this particular carbon center, out of the fluorine and fluorine, your fluorine will be having the higher priority than your fluorine. So you can see higher priority groups are present on the same side. That means the configuration it will be my Z configuration will be present around this molecule. Right. Next one, second molecule if you see it. In this case, bromine and Cl, bromine is gonna have the highest priority followed by the fluorine. And here on this side, if the mass this atomic numbers are same, you have to focus on their masses number. So out of the protium and deuterium, your deuterium will be having the higher priority. So again, the higher priority groups are on the same side, so the configuration it will be your Z over there. Right? Now in the third molecule, if I see it, so the carbon it has the more priority as compared to the hydrogen. So this order will be followed. Again, here the methyl group it will be present, and this one is again. So again, the some higher priority groups are present on the same side. So this is my Z configuration. Right. Now in this case, here you can see here on this carbon center, the carbon to which bromine atom it is attached, this will have the higher priority. The methyl will be having the second priority. On the other side, if you observe it, this ethyl group that is present, it is gonna have the more priority, and the methyl group it will be having the lesser priority. So in this case, you can see the higher priority groups are on the opposite side. So this is gonna have the E configuration. That means Z, Z and Z and the E configuration it is there. Z, Z, Z and the E configuration. That means A is gonna be the correct answer to this particular question. Okay. So now let us move up on to the next one. This is the one. It says now we have to find the total number of the stereoisomers that are possible in the given compound. So in this compound you will be looking upon to the chiral centers if it is present, and also you will be looking upon to the double bonds because around that the diastereomers can be formed, that is the cis and the trans configurations we can get. Right. So here if you see in this, the chiral center, firstly if I focus upon, I guess there is no chiral center because on this center also these two of the hydrogen atoms are attached. So no chiral center, only these double bonds are present like this. This is the one. So 1 and the 2 position it is just present. Around that cis and the trans configurations are possible. So 2 raised to the power of 2, total number of the stereoisomers you will be getting is as 4 over 10, right? That means the correct option, it will be your A over 10, right? Moving upon to the next question you have is this one. So two of the compounds X and Y has been given to us. We have to find the relationship between them. So Newman projection has been given to us. We will be converting it into the Sawhorse and then we will be converting it into the Fisher projections. Then you can see the relationships, or if you are able to observe the relationships in the Newman projections, that also it is fine. Okay, so I'm gonna convert it into the firstly Sawhorse projection. The X molecule I'm converting it. So in the first carbon center that is given, that is represented by a dot. So here this OH group it is present, and on this side the methyl group, and here is this hydrogen group it is attached to it. On the back side, two of the hydrogen atoms are given like this, and here is this methyl group, right? So this is its Sawhorse projection. To convert it into the Fisher projection, I wanted is the eclipsed conformation of it. So for that, I am doing is the 180 degrees rotation around this. Around this center, here will be hydrogen and hydrogen only, and here it will be 180 degrees inversion has been done. Here the OH group it will come. Here you will be seeing is the presence of the hydrogen atom, and here you will be seeing is this methyl. Now I can convert it into the Fisher projection. That will look like this. The first carbon atom, OH group, it will come over here. The hydrogen atom will be on this side. The methyl group, it will be on this side. Where the hydrogen, and this methyl group, it will be this. So this is the X conformations that we are observing. Now for the Y molecule, again, firstly draw its Fisher. Firstly, I am drawing its Sawhorse projection and then I will be drawing its Fisher projection. So here in this case, like this, the species is given OH, hydrogen, here the methyl group it is present. Okay. Now here you have the hydrogen, the methyl group, and this is your hydrogen group it is present. Okay. This is the one. So I want to draw its Fisher, so I'll be converting it into the eclipsed conformation. So for that, I'm gonna do the 180 degrees inversion over here. So this is the one. Here the 180 degrees inversion. Here the hydrogen it will come on this side. OH will be present over here. And on this side you will be getting this hydrogen, the methyl group, and this hydrogen atom it will be present. Okay. So now drawing its Fisher projection. So the methyl group it comes over here. The hydrogen group on this side, OH group on this side, methyl is over here, hydrogen and the hydrogen atom. Around this you can do the rotation. Methyl groups will be shifting because on this maximum number on the straight chain, the maximum number of carbon atoms it should be present as per the rules of the Fisher projection, right? This species you will be getting, and on this side also the OH group I'm bringing it on this particular side. OH is brought here, methyl is over here, and this is hydrogen, right? So this is the Y molecule that I'm getting. This is my Y, and this one was the X species. So compare these two now. So the X molecule that I was having, that looks like this. Here the methyl group, hydrogen, hydrogen. Here is this OH group is present, and the methyl group is present on this particular side, and the hydrogen is present on this side. So this is your X molecule you are having. Now for the Y molecule, the rest of the species things we have kept it to be the same. So just focus upon to the conformations. The methyl group this time it is present on the right side and this is on the left side. So you can see these both are the mirror images. So try to place the mirror over here. You can see this hydrogen atom it is reflecting your this hydrogen atom, and this methyl group it is being reflected. This one is your A chiral center only, so you cannot say that there is no mirror image to be encountered on this particular side, but for this carbon center you can observe it. So these two they are your mirror images, and if I place the molecule number X over the Y molecule, they will be non-superimposable because methyl will be facing the hydrogen atom over there. So this becomes your enantiomers. Enantiomers. Also, you can confirm it from this configurations around them. One will be having the R configuration and other will be having the S1. So you can see OH will be given the maximum priority, this one will be second one, and this is the third priority, and this one will be the fourth one. So 1, 2 and 3, this is the S configuration, but it will be interchanged because it is present of the horizontal position. You are having your H group, it is present, that is of the least priority. This is going to have the R configuration. Now in this Y molecule, again 1, this one is 2, and this one is the third one, this one is the least. So 1, 2, 3, this is going in the R configuration, but this will be converted to the S. So this is gonna have the S configuration. So enantiomers that differ in their configuration. So X is the R configuration, and Y is having the S configuration. So both of these, they are my enantiomers. So that means the relationship between these two will be your enantiomers. Okay. So now let us move on to the next question. We are having this one. In this, they are asking us the most stable conformation of the ethylene glycol. So what is basically an ethylene glycol? You have this CH2, CH2, and at the adjacent positions, the OH groups are attached to it. Okay, so this is your ethylene glycol. So you can see at the 1 and the 2 position, among these two, the Newman projection has been drawn. Whenever this OH groups type of the species is present, that can show the hydrogen bonding. Here you will be observing that Gauche conformation, it is more stable as compared to your empty conformation. The reason for that is the presence of the hydrogen bonding in there. Right? So the order in this stability you will be generally observing is that Gauche conformation is more stable, followed by their empty conformation, and the least one is always your eclipsed conformation. Eclipsed conformation, reason being there is presence of the torsional strain. Torsional strain is present. So always the staggered conformations are more stable one. So out of them you are having one is the Gauche and other is the empty. But due to presence of the hydrogen bonding, Gauche is more stable. Okay, so now let us focus upon the cases that have been given to us. You will be trying to find it out which one is the Gauche conformation over here. So in the molecule number A, if I observe, OH groups, they are present at an angle of 180 degrees to the one another. That means this is my empty conformation, right? Now in this case, in the molecule number B, if I observe, here you can see this OH group and the other one, they both are at an angle of 60 degrees to the one another. That means this is its Gauche conformation I am having, and in this conformation only you can observe this oxygen atom and this hydrogen atom, they can show the hydrogen bonding in between them. They will be having the presence of hydrogen bonding. Due to that, it is most stable one. Alright. In the C molecule, you can see here the OH groups, they are present one behind the another one. That means the angle between them, it is of the 0 degrees. So this is your eclipsed conformation you are getting it. So this is not stable. Okay. Next, so the maximum stable one, that is of the Gauche conformation. So the correct answer will be your B option you are having. So the most stable one is the Gaussian. So B is the correct answer to this particular question. Okay. Now moving upon to the next one, we are having is this. So in this case, they are asking us consider the following compound. So this is the compound that has been given. By which of the following routes that have been given to us, which one is the correct route that we should opt to form the above molecule that has been given to us. Okay. So here you can see here is the presence of the ether molecule that is present in there. And for the generation of the ether, generally we follow is the Williamson ether synthesis method. Williamson ether synthesis. Ether synthesis. In the class number 12, in the chapter that is of the alcohol, phenols and ethers, generally this is studied over there. So this is Williamson ether synthesis. So in the Williamson ether synthesis, what you generally observe is that you have the alkoxide species, that is your RO negative, and as a counter ion this Na positive it is present. This attacks over the alkyl halide species. So this is your alkyl halide species you are having, and what you see is that there is SN2 attack is observed over here. SN2, that means the backside attack it is orbit. So here what happens is this alkoxide species, they attack over this alkyl halide and this X group it leaves from here. resulting into the formation of your ether species. So you get is R, O and the R dash along with the release of NaX. This is what happens in your Williamson ether synthesis, and here as I said the mechanism that is obeyed is one SN2 mechanism, and for the various alkyl halides if you see the SN2 attack it is possible if there is less steric hindrance present around the alkyl halides. So that means in case of the primary, the rate is maximum, followed by the secondary one, and the tertiary is the least. In fact, in the tertiary, you generally observe is the SN1 because for the attack we want a less steric hindrance. So this is the order for your alkyl halides that is generally observed, and this is what we are going to focus in this particular case as well. Okay. So here you will be seeing in the molecule in the option number A, if I see here this alkoxide has been given and this is attacking over the alkyl halide which is basically your methyl iodide only. So that means there is no steric hindrance directly this O negative it can come and will be attacking over this methyl group, and this I group it will be leaving from here. That means this attack is visible one. Right? Let us compare the other ones also. So in the B molecule, this is the alkoxide that has been given, and the alkyl halide that you are seeing, the carbon on which this leaving group it is attached is further attached with the 3,3 carbon center. So that means this alkyl halide it is my tertiary center. So that means the possibility of the SN2 attack over here it is not possible. Right? Now in the next case if you see the species given are both are the alcohol species only are given to us. To generate the ethers we need one as the alkoxide and other as the alkyl halide or some good living group it should be present where both of the cases OH group it is present. So reaction again won't be visible over here. Right? Next one if you see again the OH species is given that is your alcohol and the alkyl halide. We need is the alkyl oxide species. The reason for that is alkyl oxide that is gonna be your better nucleophile for the attack over the alkyl halides as compared to the OH. No doubt here the electron density is present, but in the alkyl oxide more amount of the electron density is there, so their nucleophilicity it is more, right? So here that means this one is gonna be the preferred option for the preferred path for the synthesis of the given ether molecule. So A is gonna be the correct option for this particular question. Okay. So now let us move upon to the next question. So that is your 20th question number. So here they are asking is the major products formed in the following reaction is or are. That means here we have to consider all the possibilities for the formation of the products in this particular reaction. Okay. So the given molecule you are having is this benzene ring, to that this fused ring it is present containing an oxygen atom. So in this case what is gonna be the reaction? Let us see. So this benzene ring and here is this oxygen group. To the dash position here the Br group is attached, and here at the wedge position this Br group it is attached to it. So you can see here the oxygen atom that is containing the lone pair of electrons it can apply the NGP effect over here because this electron density it can be shifted and this Br group it can leave from here. So this is you can see here the NGP effect it can be applied. So due to that what I'm gonna get here is this benzene ring it is gonna remain as it is, and here will be this species, and at the wedge position the Br group is present as it is, and here you will be seeing on the positive side of this positive charge it will be coming over the oxygen atom because it has donated its electron pair, right? So due to the first condition that is due to the NCP this mechanism it will be obeyed. Now in the reaction medium you can see here they have passed is the methanol is passed to it, right? So in the next case what is gonna happen? The methanol species. The oxygen it bears a lone pair of electrons in the methanol species, right? So it can act as your nucleophile, will be attacking at this particular site, and this electron density it will be shifted onto the oxygen atom. Now this methanol species that is attacking over here, it has because this species that I have got, it is my planar one. No doubt in the wedge plane, this bromine atom it is present. So the preferentially the attack should be from the the bottom of the plane also, bottom of the plane only. But here, since you have to, in the options you can see the various options have been given where the attack is given from the above side as well as from the bottom side, and they have asked that to see all the possibilities which are possible in this particular question. So in that case, you will be seeing two of these species will be formed like this. Here the bromine position it is fixed, but the methanol species that is coming, it can come from the above plane, and along with that it can also come as from the bottom plane as well. That means from the dash plane also the attack is possible. Here will be the PR. No doubt the major one is this one, and this one is gonna be the minor one because of the hindrance that is present over here. So that means taking into the consideration the possibilities of the various products that we are having. Here the correct answer to this particular question, it will be your option number A, where both these products have been found. Okay, so OME group present at the dash position as well as at the wedge position will be your correct answer. Okay, so now let us move upon to the next question that we have is this one. That says the correct relative order for the reactivity of the following chlorides in the SN1 reactions. So for the SN1 reactions, basically what happens in the SN1? You have the alkyl halides. Firstly, in the SN1 reaction, the leaving group at least resulting into the formation of firstly a carbocation and the leaving group it has a lepton, right? And then the attack of the nucleophile over this carbocation species that is formed over here. So our nucleophile bond is formed over here. So that means this carbocation species that is getting being formed, the relative stability of this particular carbocation, it determines the rate of the reaction. The reason for that it lies into the fact of its energy profile diagram. If you also observe, suppose this is the initial energy of the reactants. Here firstly they require the energy and result into the formation of a stable carbocation, and then a small amount of the energy it is required that results into the product formation. So the various peaks that you observe in this. So this is your reaction coordinates. This is my reaction coordinates, and this is my energy profile energy. It is increasing in this particular order. Here my reactants are present and here is your product. So initially in the reactants you have is your RX bond it is present. This transition state, that is the first one that is present, it depicts the breaking of the RX bond. This particular point it represents the formation of the carbocation over here. Then in this particular transition state you have is the transition state showing the attack of the nucleophile over the carbocation, and at last in the product formation you get is our nucleophile bond it has been formed over here. So this is what it happens. So initially you can see the amount of activation energy that you are seeing for the formation of carbocation, it is more. So you can see this much is the activation energy for your first step, and this one is the activation energy for your second step. This is activation energy number 2. So one is more. So more is the amount of activation energy. That means smaller is the rate for the reaction. That means it becomes your slowest step of the reaction, and slowest step of the reaction it determines your rate of the reaction. Okay, so this is the crux of your SN1 reaction, right? So the energy profile diagram. So we have seen this, so we have to focus upon to the stability of the carbocations in this. So here in the first molecule when you will be seeing this Cl negative, it is gonna leave. After that, the carbocation that formation that we will be getting is this one. Here the CH2, here the positive charge it will be present, and here is the presence of this OM. In the second molecule, when this Cl negative it is gonna leave, so you can see this carbocation species you will be getting. Here is CH2 and there will be the positive charge present over here. And in the third case, the carbocation that we will be getting is CH2 positive, and here is this NO2 group that is present over here. So now in this, the substituents which are attached to the benzene ring, it is gonna create the it is gonna vary the stability of the carbocation species that we are getting. Here in the first case, the OMe group that is present, it is your electron donating group that can apply the plus N effect. So by applying its plus M effect, it is gonna donate the electron density to the benzene ring, which will stabilize this carbocation. Right? Next is here in this molecule, here is presence of the hydrogen atom only. That means no substituent I am having on the benzene ring that can apply its plus that can apply the plus M or the minus M effect to it. Whereas in the third case, when you will be seeing this NO2 substituent that I am having, this is my electron withdrawing group and it can apply the minus M effect. So it basically withdraws the electron density from the benzene ring. That means creating more deficiency at this particular site. So the stability of the carbocation it will be further decreased over to that extent. So that means the least stable carbocation it will be formed in the third number case and the maximum stable is formed in the case number 1. So that means order it will be the order of reactivity order it will be that in the first case the fastest reaction and in the third case the least one. So the C option that you see, the first one it is given that it is having the maximum and third one is gonna be the least one. So the C option is the correct answer to this particular question. Okay, so this is how on the basis of SN1 the rates have to be decided. Now the next question we have is this one. Okay, so here we have to find the major product formed in the following reaction. So here a 6-membered ring it is given to us. Here you are having two alkyl groups attached to it and at this position this OH group it is attached and in the reaction medium H2SO4 is given to us. So H2SO4 is basically a source of the proton over here. Now for the protonation you can see here the oxygen atom that I am having, it bears a lone pair of electrons upon it. So these lone pair of electrons they can abstract this proton from the H2SO4. That means we are gonna get here is the formation of the water. That means here the CH3, and here you will be getting this water formation. OH2. This oxygen has to rated its pair, so a positive charge is coming on this particular side. OH initially it was not a good living group, but after its protonation it has converted into the water. So water it is your good living group. So it can leave from the medium directly and resulting into the formation of the carbocation at this particular position. So here you will be getting the carbocation and at these two particular sites the methyl groups they are present over there. Right. So now since the carbocation has been formed and we know that for the carbocation there is a possibility that it can undergo the rearrangement to get a more stable carbocation. Right. So here the carbocation that I am getting is this carbon center is attached with the two carbon centers. So this is my secondary carbocation having. So after doing the rearrangement in this, so this is the one position and this is the two position you can say it. So 1,2-methyl shift I can do it. After shifting the 1,2-methyl shift, after doing that, what you will be getting is CH3 will be present over here and a positive charge will be formed at this particular side. So we have done is 1,2-methyl shift. So after doing the methyl shift, the carbocation that I have got, it is my tertiary carbocation because this carbon center is further attached with the three carbon centers. So this tertiary carbocation possibility it is there. That means reaction further is gonna proceed through this carbocation. Okay. Now further heating has been provided. That means elimination is gonna take place. No further nucleophile attack is possible in this. So elimination will be done in this case. So what you can do is from this side, this H positive it is gonna lose. This electron density it will be shifted. So this will result into the formation of an alkene where the double bond it will be formed and two methyl groups will be attached to these sides. So this is gonna be the final answer to your question. So now look for the options that you are having. So I can see the C option is the correct one for this where the alkene with the two methyl substituents attached on both the sides. Alright, so C is the correct option for your question. Now moving upon to the next one that we have is this one, this question. Again, the major product formation we have to find it out. Okay. So the species that has been given to us is this one. I'm drawing it into the sawhorse projection only. So here you are getting is this one. Here the OH group it is present, and here it is. On the wedge side the methyl group it is given, and on the starch side this hydrogen atom is present, and at this position we are having this pH group, and here on this side at the wedge position the hydrogen atom and this methyl. Now this has been treated with the TSCl and the pyridine. So pyridine, basically it is your base. Its role is to abstract the acidic proton. So this pyridine, it will abstract the proton from this OH end. We will be getting the formation of this species. Here the methyl group, hydrogen, and this O negative it will be formed. Here you have this pH and this H and this methyl group it will be present. Now in the other case, the TSCl that I am having, so this is your TSCl, so where this O negative it is gonna attack over here, and this Cl negative it will be leaving over here. Basically OH is converted into the OTS, that is your better living group, using this particular species. Right, so what we are getting here is will be the formation of here the hydrogen methyl group, here the pH group, and here this methyl group, hydrogen, and here is this has converted into the OTS, which is my good living group. Now this is your good living group. As compared to the OH, this is your good living group because it will be your resonance stabilized. So you get this type of the species O with the sulfur attached to it, and this benzene ring it is attached to it. So this is basically your OTS group. And the O negative charge it will be stabilized due to the resonance with this S double bond O group that is attached with the PS group that is present. Okay. So now in the next step they have given us, okay, in the next step they are asking us is that treatment is done with the NaOET in the presence of the ethanol. That is your basic medium has been provided to us. Okay, that means this is treated with the NaOET and the ethanol. So this is your solvent, and OET is gonna act as a base. That means elimination is again gonna be taking place. So OTS despite good living group. So for the elimination to take place, the hydrogen atom that is present on the adjacent carbon atom and this living group that is present, they both should be anti-pariclinal to the one another. So for that, what we have to do is in this carbon atom that is containing the hydrogen atom it is present, we have to do the rotation so that this OTS group and this hydrogen group they become trans to the one another. So its conformation we can draw it by rotating this species, rotating these molecules that are attached to it. So before treatment, I am doing this. Its conformation I am drawing it. So we will be getting this. Here the hydrogen atom, here the methyl group, here the OTS it will be present, and at 180 degrees rotation, so not the 180, 60 degrees rotation, this hydrogen atom will come on this particular position, methyl group it will come over here, and this pH group it will be present on this side. Now this can go for the elimination. So with the OET negative, that is from the NaOET ethanol mixture that I am having, this OET negative, it will abstract this particular proton from here. This electron density it will be shifted, and this OTS group is gonna leave from here. So basically you are getting is an alkene formation over here. Now we have to focus upon the substituents which are attached to it. So methyl group here you can see this is present on the wedge position. So that means on this particular carbon center, methyl group will be on this side and this is the hydrogen. And on this particular carbon center also the methyl group is on the wedge side. That means both the methyl groups are on the same side. And this other side, this pH group is gonna be present. So this is gonna be your resultant product where both the substituents, that is your methyl groups, are on the same side. So look for the option. So here you can see in the option numbers A and B you are seeing no elimination they have done it. They are converting the OH to the OET. So that is not happening over there. Right? Elimination is taking place. So A and B cannot be our answers. Now in the C and D if you see alkenes have been formed over here. In the C molecule, both the methyl groups are on the same side, and in the B molecule, they are on the transposition to the one another. That means C is the correct option that as per the product that we have drawn. Right? That means C is the correct option to this particular question. Okay. So now let us move upon to the next question. We are having this one. It says which of the following bromides they cannot form an alkene by the E2 process. So for the E2 process, as we have done it in the previous case, that for this the leaving group on one of the carbon center, and to that the adjacent position the hydrogen atom that is present, they should be at the anti position to the one another, or there should be presence of the hydrogen atom for the E2 elimination to take place. So for that, to see this E2 process, we will be discussing, or we will be drawing the structures of all of these molecules they have given to us, so that we can get to know which of the molecule is not giving the alkene cannot be formed. So first is 1 bromo 2 dimethyl propane. That means 1, 2, 3. This is the propane. 2 dimethyl. One position you are having is this Br, and at the second position 2 methyl groups are attached to the like this. This is the species that they have drawn. This is CH2 it will be there. So this is the first molecule. Right? Next is 2 bromo 2 methyl butane. So 4 carbon atoms, 1, 2, 3 and the 4. 1, 2, 3, 4. At the second position the bromine group it is attached, and the methyl group it is also attached at the second position. So this is the molecule number 2. Molecule number 2 that we are having. Okay, the first one also you can draw it in this particular form only. 1 bromo, 1, 2, 3 carbon atoms. At the first position the Br group is attached, at the second position 2 methyl groups are attached. Okay, so this is the molecule number 1, this is the molecule number 2. Now the third molecule is 2 bromo 3 methyl butane. Okay, 1, 2, 3 and the fourth 1, 2, 3, 4, 2 bromo. Second position this Br group, and the third position this methyl group it is attached over there. This is the molecule number third we are having. Okay. Now the fourth one, if you see, it is 1 bromo 3 methyl butane, 1, 2, 3, 4, 1, 2, 3, 4, right? 1 bromo, and the 3 methyl group it is attached at this particular position. Okay. So now for the E2 elimination, as we said, at this type of the species, where if your X group suppose it is attached, in the adjacent position there should be presence of the hydrogen atom, so that if a base is coming, base can abstract this particular proton, this electron density it can shift, and this X group it can leave from the base. This is what we need for the E2 process. To check this all out in all of the 4 molecules they have given to us. So in the first molecule, if I observe, on this particular carbon center, this Br is my leaving group it is present, right? But on the carbon which is adjacent to it, where 2 methyl groups are attached to it, there is no hydrogen atom is attached over here. So that means it is in the first molecule only. The elimination it won't be possible, because on the adjacent carbon center no hydrogen atom it is present. No hydrogen atom on the adjacent carbon, on the adjacent carbon atom it is present. That means the correct option is the first one only. There is no elimination. You can check it out into the other ones also. In the second molecule, if I observe, Br is present. The carbon that is alpha to it, you can see this is the carbon center, this one is the carbon center, this one is the carbon center. At all of this, the hydrogen atoms presence it is there. Where these hydrogen atoms are present, so elimination it is possible over here. So E2 is visible. E2 can take place in this. Next is in the third molecule. Here you can see this methyl group is present at its adjacent position, and this contains the hydrogen atoms. Also on this carbon center, also the hydrogen, this alpha center, the carbon is containing the hydrogen atom. So E2 is possible in this particular case as well. In the fourth case also you can see this one is the carbon which is adjacent to the carbon center, to which the leaving group it was attached. So here this hydrogen presence, it means there will be the possibility of the E2 will be possible. That means it is in the molecule number 1, where in the alpha position no hydrogen atoms are present, where the E2 elimination we can carry it out. So the correct option to this particular question, it is your option number E. Okay. Now moving upon to the next question, we are having this one. It says the major product formed in the case of following reaction is. So the reaction given is this one. So the species that, let me just draw this. We are having this CH3, CH3, okay, this is further attached with the nitrogen, that is attached one with this methyl group, that is CH2, CH3, and this is attached with the methyl group, and this is pairing a positive charge. So this is my good living group actually, and this is treated with the OH negative. So again an E2 reaction only it is being observed over here. So you can observe it like this. CH3 carbon that we were having, we can write it as CH2 and the H species you can attach it. So this is the carbon center that is bearing, this is your living group you are having over here. Now to this carbon on which the living group is attached, next carbon you have to focus, and there should be presence of the hydrogen atom over there, and this is present over here. So that means E2 reaction will be observed in this case. So we are having this E2. So this OH negative will come, abstract this proton from here. This electron density it will be shifted, and this bond it is gonna break. That means your nitrogen group it will be leaving from medium. So we will be getting, here is the formation of CH2 double bond CH2. So this alkene is gonna be the final product to your reaction. Okay, so that means the correct option to this particular question is the option number D, where the ethene molecule it has been formed. Okay, so this is the correct answer to this question. Moving upon to the next one we have is this case. So in this case alkene is given. We have to again find the major product of this particular reaction. So alkene is given and the HCl molecule is given to us. Okay, the molecule is this four-membered ring containing here the substituent methyl one, and here this species it is attached to it, and this is treated with the HCl. So this species, what it is gonna happen, the pi electron density of the alkene species that I am having, this will go abstract this proton, and this Cl group it is gonna leave, resulting into the formation of your carbocation. So this four-membered ring, to this the methyl group it is attached. Here at this position, the electron density has been shifted, so positive charge at this position, and here the methyl group it will be formed. Reason for this is that the carbocation that is formed in this particular case, this is gonna be more stable as compared to the other one. The other possibility of the shifting is you are having this one. Here the carbocation, this hydrogen, suppose it has shifted over here. The carbocation you will be getting here is the primary one, but in this case you have got as the secondary center. So that is why this carbocation will be preferred one. Okay. Now further reaction will be proceeding through this process. So here you can see this carbocation we have got it. Now you can see whenever there is a possibility that you have a four-membered ring and to that a carbon is attached where a positive charge is present, this can undergo the expansion of the ring, because reason being the three and the four-membered ring they are your highly strained one, right? So this is the alpha carbon center and this is the beta. Alpha and beta means the carbon which is next to the carbocation. So what you have to do is break this alpha beta bond. This electron density it will be shifted. Ring expansion is taking place. Alpha will carry the positive charge and beta will form the bond with this carbon center. You can do the numbering also for this. You can see this is 1, 2, 3, 4 and the 5. That means in this particular case I'm gonna get as a 5-membered ring it will be formed over here. This is number 1 you can say, this is second position. At the second position one methyl group it is attached and this was my alpha center. As I said, to the alpha center a positive charge it will be coming. Right? This is the second carbon, this is the third, fourth and the fifth. The fifth position and the position where the carbocation initially it was present, they are gonna form the bond in between them. So this carbocation that you have got is in fact your tertiary carbocation you are getting, and also the ring strain that was present it has been released over there. So in the next step what is gonna happen? the Cl negative that was we were having, it is gonna act as a nucleophile and will be attacking over this particular carbocation species. That means we will be getting the product as this one. Here is this methyl group and this Cl group it is attached over there. So this is gonna be your product, and also one methyl substituent it was left, so that will be present at this first position, it will be attached. So this is gonna be your final product. Now you can cross check your answer with your options. So in the first and the A and the B molecules, 4-membered ring has been written, so these cannot be your answers. Next is 5-membered ring. In the C molecule, we are having methyl with the Cl group and methyl with the Cl group. So this is correct matching to our answer that we have got through the mechanism. Right? So this is gonna be the answer to your question. So the correct option is your C1 for this particular question. Okay. Moving upon to the next one we have is this one. Again, you can see the major products X and Y. So two different reactions have been given to us. We have to find the product state, product formation in this case. So again, the alkene is given to us and the HBr addition has been done in both the cases. So let us see how is the reaction gonna proceed one by one. This is OCH3 and this is the alkene species. So here this HBr addition is being done. So again what is gonna happen, this pi electron density that I am having, this is gonna go for the attack over this particular hydrogen center and this Br group is gonna leave. So here a carbocation will be formed. So here the possibility of two of the carbocation species that is there. One is this species. Here the hydrogen atom has shifted on this particular side. Along with that, you are gonna get here the OCH3, and on this side the possibilities that hydrogen has shifted and the positive charge is formed on this particular side. So now the relative stability of the carbocation will be deciding through which pathway the reaction is gonna proceed in the further direction. How is it gonna proceed? So here in this, if you see, so this is, you can say A possibility and this is your B. Among these two, your A carbocation is more stable. Reason B, this oxygen atom it wears the lone pair of electrons and this can apply its plus M effect over here. So due to the plus M effect of this OCH3 group, this carbocation it is more stable. That means out of this A and B, the reaction is gonna proceed with the A path. Okay, so that means in the further next step what is gonna happen, the Br negative that was left as a nucleophile will be attacking over this particular carbocation. Okay, so I'm gonna get here is that the Br it has substituted at this particular site which is next to this OCH3 group and here this hydrogen has been attached. So this is gonna be the product for your product number X that you are gonna observe. Okay, so you can cross check your answer and try to eliminate the options. So in the A and the B, I see it that in the carbon center to which the OCH3 was attached, to that carbon only the Br group is getting attached in the A and B. C and D, it is at the next carbon center, so this cannot be your answer. So these two eliminations you can do it. Now let us see for the Y molecule that is given. Y product formation, what is gonna be the there for this case. Now the substituent they have just changed it like this. Here the alkene was present. Here now the substituent you are having is OC double bond OCH 3 group it is attached. And again the treatment of this molecule has been done with the HBr. So this pi electron density again it will be shifting, abstracting this proton and this Br group is gonna leave. So again you will be seeing is the possibility of two of the carbocations possibility it will be there. One is this one OC double bond OCH3, here the hydrogen group it has shifted, and the other case you will be seeing is the possibility is this one OC double bond OCH3. Hydrogen group has shifted on this side of the alkene and positive charge is formed on this particular side. Right? Now in this case if you see the OCOCH3 group that you are having, or it is a group that is your C double bond OCH3. This is just a second. The group we are having is C double bond O and this O group that we are having. C double bond O and this O group is attached. So this is the one. Here also it is marked. C double bond O, O, C, O, CH3 group. So this is the group that is attached to it. So now you can see here in the adjacent is the adjacent to the carbocation in the molecule number A, and this is B if you see. The A1 that you are seeing, the carbocation, adjacent to it is the presence of the electron withdrawing group that can apply the minus M effect over here. That means it is gonna withdraw the electron density towards itself. So it is gonna further destabilize my carbocation. In the previous case, it was the plus M effect that was being applied over there. So that was providing the stability to my carbocation. But here it is the reverse of it, that is electron withdrawing group is attached. So that means further away is the carbocation we are getting is better will be the faster rate of the reaction. Right? Better will be the rate of the reaction. So in that means the B molecule through the B pathway where the carbocation is at the further distance from this electron withdrawing group, the reaction is further gonna proceed through this pathway. Right? So that means in this case further the Br negative that was as acting as a nucleophile will be attacking over this particular carbocation. That means the final product I'm gonna get here is this species. Okay. So this species is remaining as and at this position your Br group and here your C double bond O OCOCH3 group it will be attached. So this is gonna be the product in this particular case and this is your product number. Product name is 1. Right? So the correct option for this it will be when the Br group is further away. In the option number A, if you see here the Br group, they are saying that it is adjacent to the electron withdrawing group. That means this one is not gonna be our reaction pathway. The correct option will be the option number B where the from the electron withdrawing group, Br group is further apart from it. Okay, so this is gonna be the correct answer to this particular question. Now moving upon to the next one you have is this question. It says the major product formed in the reaction of 3-phenylpropene. 3-phenylpropene, that means 1, 2, 3 propene, 1 carbon atom at the third position my pH group it is attached. 1, 2, 3 and 4 CH2 CH2. So this is the species that has been given to us. This is treated with the HBr. Again, alkene electron density it will be shifted. So alkene is gonna firstly abstract this particular proton and Br group is gonna leave. So again possibility of 2 of the carbocations will be there. The relative stability of the more stable carbocation we have to see it and through that pathway the further reaction is gonna be proceeding. So I'm gonna get here is CH2, CH, CH3. One possibility is that I'm getting is this carbocation and the other possibility is I'm getting is CH2, here the pH, CH2, CH2 and here will be the positive charge. So the possibility is this one. So I can see here that in the first case that this is the A possibility and this is the B possibility of the carbocation. A1 is the more stable carbocation. More stable carbocation I am having it. Okay, because here you can see adjacent is this groups that are attached to it. So that means reaction is gonna proceed through path number A. Now the Br group it will be attacking over here, resulting into the formation of the CH2PH. Here the CH, here the Br group it will be attached, and here will be this methyl group it will be attached to it. So this is the product that I'm gonna get in this particular case. So this becomes the product is the first option it says it is 2-bromo 1-phenyl propane. I guess this is the correct one. So if I do the naming from this side 1, 2 and 3. So 2-bromo 1-phenyl and the propane species I'm gonna get it. Next is okay. So it was no. This is one thing we have missed it that it is in the presence of the hydrogen peroxide. This we have listed over here. So this is with the HBr we are observing, but with the HBr with the hydrogen peroxide NTM rule you have to follow in this case. So that is through the radical mechanism it is gonna proceed. So it is in the peroxide case. Right, so in the peroxide what you have to do is that the negative part of the Here the NTM rule you have to observe it. NTM rule is observed, according to which the negative part it goes to the carbon center, which is containing the which is less substituted basically. So the final product you will be getting is in this alkene you can see this C carbon center that I am having, it is less substituted one. So the Br group it will be attacking over this particular side. So CH2Br, and this is gonna be the product over here. So what's the name of this product? So 1, 2 and 3. So we are getting is 1 bromo, 3 phenyl propane. So the correct answer is the option number C. So this HBr in the presence of the peroxide it was given. So that I missed it in the first step. If it had been with the HBr, in that case A would have been our option. But now here since the peroxide was there, so NTM rule we have to observe in this case. Okay. So C is gonna be the correct option for this. So now let us move up on to the next question we have is this one. So here the alkyne species is treated with the water, your H2SO4 and your HgSO4. So here how is the reaction gonna proceed? pH with the carbon and this alkyne and this pH group is attached. When it is treated with the HgSO4 in the presence of the HgSO4 in the presence of the acid we are having. So this alkyne group it is gonna be abstracting it. So we will be getting is double bond C pH, and here this 3-membered ring it is formed over here. Now in the next step the water molecule it attacks over there. On both the sides are symmetrical. So either of the sides the attack is feasible. So after this attack of the water and the workup we will be getting is that pH. See on one side this OH group, this alkene group, carbon and this pH group. On the other side you will be having is the presence of the hydrogen that is from the acid group that is added to it. So this workup has been done. So this is the enol form that I am getting it. This is my enol form. Further tautomerism is possible in this. So this oxygen bearing the lone pair, this can show the resonance like this. So tautomerism is being done. Tautomerism. So keto form you will be getting is as PHC double bond O, here the CH2 and this pH group it will be attached to it. So this is gonna be your final product you will be getting it. Okay, so this is gonna be the answer to your question. So they match the options now. In the A and B, they have taken the SO3 attack, SO3H attack. So that is not possible over here, right? This is not gonna be the answer. The correct option is the C1, where we are getting the pH, C double bond O, CH2 and the pH after the attack of the tautomerism. This reaction is gonna be proceeding. Okay. So this is the correct answer. Now moving upon to the last question of the day. This is the one. This says the major product formed in the reaction when N-N-dimethyl aniline. What does this N-N-dimethyl aniline it means to us? So this is your aniline molecule. Now here they have done a substitution over the nitrogen center. N-N-dimethyl. It means on this nitrogen center, instead of the hydrogen atom, now two methyl groups are attached to it. This is the N-N-dimethyl. This is my N-N-dimethyl aniline. Okay. Now this is treated with the mixture of H2SO4 and the H2SO4 and the HNO3. Basically the nitration process they are trying to do it. So during the nitration process, what basically happens in case of the aniline type of the molecules, this nitrogen atom they contain the lone pair of electrons, and in the reaction medium we have is the presence of the acid over here, right? So due to that, what happens, this nitrogen atom that is containing the lone pair of electrons, it gets protonated in the presence of the acid. So you will be getting here is the formation of this particular species, NH, here the methyl and this plus group it is present. So this species it is getting this N-dimethyl aniline it gets into the protonated form of it. So initially what we were expecting is that N-dimethyl aniline it should apply the plus M effect to the benzene ring. Due to that it should be orthoparadiol, right? Because like this whenever the nitrogen species I am having this NH2 group it is present, so this double bonds we can show it. This nitrogen containing the lone pair, this electron density it has shifted at the ortho position you are getting is the presence of the negative charge presence you are getting. That means electrophile preferentially it can attack at the ortho position or further after the resonance if you see it, the negative charge it will be coming at the para position to it. NH2 positive. So this is what we were expecting it to be. But in the presence of the acidic medium, what happens if it gets protonated? So instead of applying the plus M effect, it now applies the minus M effect to it. Because here the nitrogen, that is your electronegative species, it carries the positive charge over it. It wants it that the positive charge over the electronegative species should be neutralized as soon as possible. So due to that, what happens it withdraws the electron density from the benzene ring by applying the minus N effect to it. Okay. So due to that, what you will be observing is a positive charge will be coming at the ortho and the para position to it. So we get here is NH, Ne, 2 I was having. So this electron density it has now shifted. So somehow this charge it is being neutralized. So during this resonance I am seeing the positive charge is at the ortho position and you will be seeing at the para position to it the positive charge you will be observing it. So this is Ne, 2 we will be having it. Okay. So here the positive charge it is coming at the ortho and the para position. That means further electrophile if it is to be attacked, if it is attacking, it will be attacking at the meta position now because at the meta site no positive charge electron density it has been formed over there. Correct? So that means here the electrophile attacks at the meta position. Meta position it is will be attacking over there. Now for the this nitration when we are doing, what is the electrophile? That is your NO2 positive. Reason for that, this H2SO4 plus the HNO3 mixture when you are having, this is gonna behave as the acidic mixture. So in that what happens is this HNO3 that I am having, this goes like this. Here the OH group it is present. Now in the presence of the sulfuric acid, this H positive it is present. So the OH group that is present, it gets protonated in the presence of the acidic medium. We get the formation of NO. Here the OH2 positive it will be formed. Now water it is your good living group, so it can leave. Along with that, you get is the formation of the electrophile that is your NO2 positive. So this is my electrophile that has been generated and goes for the electrophilic substitution over the benzene ring now. So in this case, what you will be observing that here the NN dimethyl species that I was having, in the case of acidic medium, it has got protonated. Now in the for the nitration, the nitrating mixture that is present, it will give me the product as the meta position. The substituent it will be attached to it. Okay, so this is what happens when you are doing the nitration of the aniline type of the species, be it your substituted one that is over the nitrogen center or the direct aniline species. Due to the acidic medium, it gets protonated and it applies the minus M effect over the instead of the plus M effect. That means the meta substituted product. That means the correct option you will be getting is the A option. You will be observing that. Here the double bond it has missed, so this double bond it will be also present. Okay, in all these cases, right? In the A molecule it is at the meta position, B they have done it at the para, and C at the ortho position. Ortho para direction it is not observed in the case of the nitration because of this acidic medium that we have provided. Okay, so this was the last question for today. So first 30 questions of your organic chemistry part number 1 we are done with that. So I hope I have tried to explain all the questions in the detail. So I hope all of these questions are clear to you. But if you still have any doubt at any of the questions that we have discussed so far, that you can ask me in the comment section. I'll surely reply to that. And if you have come till here, That means you have been understanding these questions. So make sure you subscribe to the channel so that whenever next part I am uploading of this, you can get notification of that and you can have a flip to that questions as well. Okay, so make sure you subscribe to the channel and do hit the like button also for the video if you have understood the concepts, and do share it with your friends as well. Okay, so that is it for this part. Now we will be continuing the next part in the next questions from the next part now. Okay, thank you so much for today. So I'll be meeting you in the next video now.